So in the last classes what we have done is we have talked about CNN architectures, and even though these architectures are very different from each other, there is one thing that all of these architectures have in common. So that thing is basically these architectures, even though they are very different, they are made different by different teams, they have been released in different years, their main task, the main goal of these architectures have been classification. So what classification basically means is you have an image. So let's say this is a image of a cat. So now you might have several options. So here you have dog, you have cat, and you have rabbit. So the main task of classification is basically from this image it has to identify this is an image of a cat. So this has been the the important task about classification. So all these architectures that we are seeing are basically, even though they are very different from each other, they are all used for the same purpose, that is classification. So what today we will be doing today is we will be going practically of how to use this. Every time we come over with some neural network, something new, we will understand how to use that practically. Like we understood how to use multi-layered perceptron, now we will understand how to use CNNs to understand, to do the whole thing. That means we'll go through the code and we will understand how to do classification. So once that we have done with classification, the next thing that we will go is understand detection. We will talk about the differences. Obviously, I am not going to leave you in the dark. We will talk about it later on. But yeah, for now, we will be doing this classification using a basic CNN. And once that is done, we will go through a project of transfer learning. So in that project, we will talk about how transfer learning is executed in code, and that will also be a project for us. Okay, now let us look here. So here we are showing the basic TensorFlow version, which is 2. So we are using TensorFlow 2 and we will be solving the whole thing using errors. What you can do is, once all this has been done, you can try solving this thing using TensorFlow 1. But for now we will be using Keras because it is way too easy to do the whole thing. Now this is our CNN overview. So this is an input image, and then this is followed by one convolution which is followed by pooling. Now this is not our CNN architecture that we will be using here. This is just a basic CNN architecture. So you have the pooling, you have the convolution, and finally you flatten the whole thing out and you have the output layer. So what that means is basically you have an input and you have to, so the whole task of classification, right, in the whole task of classification, whenever we have seen the basic CNN architectures, all the architectures, AlexNet, VG or anything, at the end what they do is they increase the number of feature maps, decrease the number of dimensions, and once that has been done, they flatten the whole thing out, and once it has been flattened, they form dense layers across it. And the reason why after flattening it out we directly do not go for an output of 10 neurons, now the reason why 10 is because we are doing the MNIST dataset here, and MNIST dataset has basically 0 to 9 as the values. So the reason after flattening out is, see, flattening increases the number of neurons, so you will get a very big vector here. So the vector is very huge, so you cannot totally all of a sudden go to from this to an output layer which has 10 neurons. You have to gradually change it with time. So you have this, you can change it to, let's say, 1000 neurons, then you can decrease it to, let's say, 512, and finally you can come to 10. So you have to do this gradually, not all of a sudden in haste, right? So that is why here, instead of having one, you always have 2 to 3 fully connected layers. Even when you were talking about architectures, right, where they use 1000 class classification for ImageNet or Cephar or anything like that, even then they had 2 to 3 layers to connect to each other till you get the final thing. By the way, whenever you see this cross, right, between two layers, this means it is fully connected. Now let us look into our MNIST dataset. Obviously you know all of this in MLP. When we were talking about MLP and we went through the code, we understood the whole thing that was about the MNIST dataset. But let us have a look once more. Okay, so this is our MNIST dataset. They are handwritten digits and the dataset contains 60,000 data points. So 60,000 data points are there for training and we have 10,000 data points for testing. So once that testing and training has been done, what happens is you have an image of 28 cross 28. So if you remember, you have this whole thing. So you have an image, this is 28. So the reason why we are using CNN and the problem that we had with MLP was, if you remember with MLP, the thing was you had the image and you used to flatten it out, and then after flattening the whole thing out, you were using dense layers one after the other, dense fully connected layers. FC means fully connected. So the problem that I said was, see, this whole image is basically two-dimensional image, right? So we need to actually take into account these two different dimensions, and then we have to use that, take into consideration the second dimension, and then make a neuron out of it. Here straight up without doing anything, we are flattening the whole thing out. So that is now not how this works. So the thing about CNN is basically you can actually take into consideration the two dimensions while creating the whole network. That was the whole point why CNN was actually made. And not even that, even when you have the 3 RGB layers, even then you can use convolution to actually understand the whole thing. So even then what they will do is they will take into account the different so you will have 28 3 if this was an RGB image. So even then what they will do is they will take into account this 3 channels here. So that is the good thing about CNN, and that is what we are going to use here right now. So it has 28 cross 28 pixels and the values right from 0 to 1, and then you have the whole thing. So you have 0 to 255 as the values, since this is a black image and on top of that you have a number written, so then accordingly it will have values. So for black it has 0, I suppose, and for white values it has 255, and for any gray shades it is between 0 to 255. So here what we are doing is we are doing a basic import. We have NumPy, we have CV2, which means OpenCV, then we are importing matplotlib. Now we have two things that I told about, that is keras.models and keras.layers. So these two things, from keras.models we define what type of model we require. Since here we are importing sequential model, so what that means is, see, sequential basically means you have one layer which is followed by another layer which is followed by a third layer and so on. So this is a sequence. So this is a sequence, a sequential layer. So we are importing this kind of model. So the model that we will be creating will be a sequential model. That means the layers are one after the other. Now we will be importing the layers. So in layers we are importing a dense layer, a dropout layer, activation, flatten. So a dense layer is basically what was used in an MLP. So dense layers are basically used to create fully connected layers, right? So that is what dense layers mean. Then you had dropout layer, I suppose. So in dropout basically means thinning out of the values. So if you remember, let's say you have like this and you have 2 neurons here and all of this is connected, right? So dropout basically means that you will be randomly dropping out values. So let's say my dropout is 33%. So what that means is, out of these any one will be removed, and once that is removed you will be working with the rest of the connection. So this and this will be used, no longer will be used this. So what that means is basically you thin out the layers, or thinning of the layers is done by dropout. This is used to prevent overfitting. And then you have activation. To add activation, obviously we won't be needing that. And then flatten we have. So flatten basically what it does is, say here you have all these dimensions, and finally to get the classification part, the convolutions are used to get the features. Once you have the features, you can flatten out the features and use those features as input for a fully connected dense layer, model, and that gives you the output. So this is the whole basic structure of a CNN architecture. You have so this is for obviously classification and not detection or anything, but for classification the whole CNN architecture is basically you have the input, and then you have 2 to 3 convolutions followed by max pooling or stuff like that to get the final feature maps. So feature maps are basically all the features that have been extracted from the input. Once we have those features, we can pass it through fully connected model, a small fully connected model, to get the final output. So that is the whole thing about CNN for classification. So flattened, basically what it does is, once you have all the feature maps, you can flatten those features out so that it can be passed through this dense layers, right? That was the whole thing. Okay, the next thing that we have after this is yeah, from keras.layers we were importing convolution 2D and max pooling 2D. So these two convolution layer 2D and max pooling 2D are basically layers that we will be using and adding to our already dense model. So we have a dense model that we were using, we are adding convolution 2D and max pooling 2D. These two are layers that we will be using. Then you have from keras import utils. Utils is basically used to plot the model. If you remember, we did that last time also. And np.utils, this is basically we will be using it to convert it to categorical value, all the numbers to categorical. We'll come to that, right? And finally we are loading the MNIST dataset from keras. So one good thing about keras is, right, it provides us some random datasets from the beginning. Since the datasets have been randomly provided from the beginning, what we can do is we can use those datasets to actually work with our problems. Later on what we will do is we will not be using random pre-made datasets from keras that are present in keras. We will be understanding and going through other datasets for which you do not have to load datasets like this. You actually have to work and understand and go through each and every folder. We'll come to that later on obviously, but for now this whole thing we will be loading the dataset from keras itself because it has the dataset, so why not use that? So MNIST.load dataset, and this gives you actually two values, one for training and one for testing. Even in training and testing you can divide it into x values and y values. Y are the labels, so the labels are basically what value you will get as output, and then you have x train. Okay, then you can skip this. So here you have is basically to plot out the values. So this was also there in the MLP. What we are doing is we are using subplots. So we are using 10 columns and the figure size is 20 cross 4. You know all this because you might have learnt about matplotlib and everything. Now for the range of 10 we are plotting each and every value. So the title is set to whatever label that we are having and it shows each and every value. And once that is done, so this here for axis we are setting as visible 0, false, that means we will not be able to see the axis value. So the whole grid thing here will not be able to see. So this is basically the whole thing. This is basic matplotlib, you all know that. We don't have to go through all of this in details, right? Next what we are doing is we are going to change the shape of x train to 28, 28, 1. We'll understand why that is happening. First let us look into the actual shape of x train. So this is an actual shape of x train. So we have 60,000, 28, 28, right? 60,000 basically means the number of training data points, right? 28 and 28 basically is the width and height of our image, right? This and this. We are changing this shape. So we have train shape, x train shape 0, shape 0 is 60,000, followed by 28, 28, 1. The reason why we are adding this 1 is, see, you have an image. Now it has only one channel, right? So you need to take that also into consideration. It has one channel, that is the black and white channel. So if it had been an RGB image, so in that case what would happen is it would have 3 channels, right? So here you would have 3 channels and then the shape would have been 60,000, 28, 28, 3. But since we are having just one channel, we need to convert this into that actual comma 1, so that the model knows, okay, so 28 comma 28 is the height and width, and this represents the channel number. It is important to change the shape to this. Alright, so we are changing the shape now. So earlier what we were doing is, if you remember in MLP, what we were doing is, see, in MLP we were straight up adding a flattened layer in the model itself. So you had a 28 cross 28, it does not matter because it was whole going to be flattened out to form a 784 dimension vector, right? So it was totally being converted into this. But here we have to make sure that the shape, original shape, gets retained. Hence we are adding a comma 1. So that means we are adding one black and white channel. So if you run this, see, now the shape has changed to 28 comma 28 comma 1. This here is basic pre-processing of an image. So if you see here the actual values, see, all these values are integer values, 0 0 0 0 0. Okay, so what we are doing here is basically we are converting these integer values into float values. Now why this we are doing is so that it becomes easier when you are convoluting the whole thing, if your input and output are of the same data type. So we are converting train and test to float 32. Then we are normalizing the whole thing. So what that means is, when you have numbers, the colors, you have them in this format, 0 to 255. So the colors lie between 0 to 255, 0 representing black, 255 represents white. So what that means is, now we are dividing the whole thing by 255. So the 0 will still remain 0 and it will represent black only. The 255 will get converted to 1 because 255 by 255 equal to 1, and this will now be white. So that means now instead of 0 to 255, our values will lie between 0 to 1. Okay, this is the whole thing basically of dividing the thing by 255 to normalize it. Once that is done, we will convert the y train and y test to categorical values. So what that means is, see, when you look at the original y test, right? So let's say original y train, let me look at that. So our y train is basically an array here in this format, right? If you look at the shape, see, it is basically 60,000 comma nothing. So what that means is, it is 60,000 and the output is basically in this format. Let's say y train 0, so it is 5. When we are putting this value into our model, our neurons, so what will happen is, see, our output, like we said, should be a 10 dimension output. So here you have this dense layer and you have neurons, right? So this should be 10 neurons. Each neuron should represent, one neuron should represent one number. So when you are doing a softmax, what will happen is, it will give you, suppose this neuron represents the number 0, this represents the number 1, this 2, and so on. So let's suppose I am doing a softmax. So what this will give me is the output, or the chances, or probability, better word, probability that the input image is basically 0. So let's say our input image is 3. So this here, this neuron will give me, let's say, 0.001. So the chance that this 3 is basically a 0 is 0.0001. In the same way, here it will have less value for 1, for 2, and for the third value it will have very high. Let's say it has 0.9. So that means, yeah, it is 90% probability that this input image is a 3. So that is found out using this neurons. So what we are doing is basically to understand this value, since we have just 5 here, so we cannot use 5 as an input or an output, right? We need to change that. So what they have done is, they have converted this into a categorical value. So now you have, for 5 you will be having 0 0 0 4 5. Instead of 5 you will have 1. Then this represents 6 7 8 9, right? So this will be our data set, our output. Our output will look like this, and Here you have all zeros except for the place in which 5 is. So this is for 0, 1, 2, 3. Okay, so you will have one more here, 4, and then this is for 5. So in the fifth place you have 1 because this whole value belongs to number 5. Okay, so you are converting it into categorical value. You got this? So we are going to do that now. Once that is done, let us look at the value now. So our y train 0 was 5, right? Now let us look into how our 5 looks. So you have 1, so this represents 0, this is 0, this represents 1, 2, 3, 4 and 5. See, in the fifth position you have 1, other positions are all 0, and the data type is float 32. To keep the data type similar, we are converting our input also to float 32, right? Also, one thing that you need to know is this also represents the probability. So when we are calculating anything, right, so we have actual value versus predicted value. So the actual value, if in the softmax we are getting the probability that it belongs to a particular number, in the in the predicted value, if you are getting the probability that it belongs to a particular number, in the actual value this is the probability that it belongs to 5. We know 100% it belongs to 5, hence this probability is 1 and the rest is all 0. So what our main task is, basically when you are getting the output in the softmax, you will be getting it in this format: 0.01, 0.02, something like that, and in the fifth position you will have 0.9, 0.01 and so on, like this. Okay, you will have a whole array of this format. So your main task is, instead of this 0.01, 0.02, this should come down to 0, as close to 0 as possible, and this should come down to 1, as close to 1 as possible, because our input is in this format, so we want the output also to be in this format. So what that means is, from the values that are not possible, the wrong values, and the correct values, the difference should be very high. By the way, this should not be very surprising, because all of this has already been done when we were talking about multi-layered perceptrons. When we were building a multi-layered perceptron model, we have done all of this. The next part, that is the building of model, actually this is a new part, because we will be using a convolution model here instead of a basic multi-layered perceptron model. Okay, so this is the new part. So whenever you start or describe a model, you always start by giving what type of model here it is. So this is a sequential model. So we have sequential model equal to sequential, right? And I explained what sequential means. This is basically one after the other. When it is in sequence, we have a sequential model, right? So once we have described what type of model we will be using, now we add layers to it. So the first we are adding is a convolution 2D, then we are followed by a max pooling 2D, then we are adding flatten and 2 dense layers. But first let us talk about this convolution 2D. So let's come back to convolution 2D, right? So the first parameter in convolution 2D is the number of filters that we will be using. If you remember, what this means is, see, we have an image of 28, 28, 1, right? So number of filters basically tells us the number of kernels that we will be using. So we are going to use, in this case, if you see here, we are using 32. So we will be using 32 number of filters. So what that means is, the number of filters also tell us the depth that our model will be of. So the number of feature maps that you are going to get. So let's suppose everything else does not change. Okay, so let us suppose our padding is same and we get this output 28, 28, but here instead of 1 you will have 32, because 32 represents the depth, and this number is also determined by the number of filters, and the number of filters are given in our first parameter, and that is given as 32, right? So that is what our first parameter stands for. Second is the kernel size, 3, 3, because since all the filters that we will be using are 3, 3. So this is our kernel size and we will be using 3 cross 3, right? So this is what that means. The second parameter is our kernel size, right? Then what we have next is activation. So we will be using a ReLU activation here. So our activation basically means that after convolution, see convolution, if you remember, I told about this also again and I'm saying again. So when we talk about convolution, what this basically means is first we have the multiplication of the values and all those values are finally added up, right? So this is basically what a linear model should look like. So to add non-linearity, we always need to add an activation function. So the activation function that we will be using is ReLU function. We do not have to worry about ReLU causing the problem of gradient descent or gradient descent, I'm saying gradient explosion or vanishing gradient problem, because we have just one convolution layer and our model is very small. Then this is followed by kernel initializer. So if you remember, we talked about something known as weight initializers, right? We had weight initializers. So weight initializer was basically when you had all these weights in MLPs. So you had Wx plus B. B was the bias. So the W's that we were using is so this was basically summation of I equal to 1 to m or something like that. So what this W means is basically the weights that we will be using. When we firstly start the model, build the model, we randomly initialize the weights, right? So these weights can come from a normal distribution. So weights can come from a normal distribution, or it can come from some other format. So here also these weights are basically kernels this time. So instead of one weight, you have all these kernel values. Now these kernel values, now they will come from a Hay weight. Is it a Hay uniform distribution? Okay, so they will come instead of a normal distribution, they will come from a uniform distribution, right? So the kernels are randomly initialized with uniform distribution. And then you have the input chip. So this gives you the input chip. Initial chip that we will be using is 28, 28, 1. The reason why we have 1 again is because we have one channel, the black and white channel. So we need to convert that. And also one more thing, interesting thing that came into my mind is, see, we are using something that is known as convolution 2D. So why this whole concept of 2D? So this D basically means in how many directions the convolution or the kernels can move. So you have the input here, right? And then you are convoluting it with this kernel, okay? So you place the kernel here first, then you shift it in this direction and you get the whole value. At the same time, you will also shift it in this direction, right? So since our kernel is being shifted in two different directions, we have convolution 2D. Hence the name convolution 2D. So if you will be shifting the kernel in one direction, it will become convolution 1D, and in three directions and it becomes convolution 3D. So depending upon what you are using, you need to change this value, right? This is followed by a max pooling layer. So max pooling, if you remember, again max pooling is 2D is because of the same reason that it moves in two different directions. The kernel will be moving in two different directions. So what that means is, see, you have this here input, and even though in the kernel there is no normalization because you don't have to normalize it. When you write 2 cross 2, that means of every 2 cross 2 value in the input, you will be finding the maximum max pooling of that. So what that means is, so it is 2 cross 2, right? So you have the input here and you will be placing the 2 cross 2 here. So let's say you have 1, 2, 3 and 4. So in the first value of our output, we will get 4. Then it will shift to this direction, right? So now you have 2, 4, 3 and 1, right? Suppose you have this, okay? So now the value will become again 4. So again you will shift it here, right? You will shift it by one stride. Now you have 3, 1, let's say 0, 2. So here you get the value highest as 3. So this is basically max pooling, and since max pooling happens in both directions, so when you represent 2 cross 2 here, right, so that also means the kernel size. So for every 2 cross 2 you will find a max pooling. That is what this means. And again max pooling 2D is because we are moving it in this direction, but at the same time the next time we'll be moving in this direction to get and fill all these values up, right? To fill all this up, we will be moving in both directions. Hence you have this whole thing of max pooling 2D. Next we are flattening it. So make sure here, since this is a very easy task, right, so we are using only one convolution layer followed by one max pooling. If your task increases, then you will be able to add, you will have to add actually more convolutions. So you are flattening out it. So that means Now you have extracted all the features that were required. Now you will flatten this out, and you have one dense layer of 100, because we do not want to abruptly change the whole flattened out value to 10. So we first change it into 100, and then finally we have 10. In 100 you have an activation of ReLU, and this is followed by a kernel initializer, right? So kernel initializer is a Hay uniform here. So you will have this fully connected layer FC, and here all the weights will be randomly initialized from Hay uniform, right? So that is what this means, kernel initializer. And finally dense model. Here you cannot give activation as anything else other than softmax. The reason why is softmax, what it does is, softmax, it converts random values to probabilities. So if you want the probability of this particular image belonging to a class 0, so to get that probability we use softmax. So all the values that you will have here, right, after activation obviously, so you have all these neurons, so they all give out some probability. The interesting part of this is, after you add all of these probabilities, the whole value is equal to 1. So that is why we use softmax. So the reason why we are using softmax is to get random probability values, right? Instead of getting values, just random values, we want the probability that it belongs to a particular class. Hence activation is softmax. Here you cannot change the number of output neurons that you will be using. This has to be 10 because our values are from 0 to 9. So this has to be the same, you cannot change this. Now you run this. Now let us see the model summary. So like you can see that adding one convolution layer and you have 500,000 of trainable parameters. So that is a lot. Hence to avoid that, we have all those concepts of dropout and regularization and everything else, right? Then you are using utils.plot model to plot the value. Here you can see you have question mark which is followed by 28, 28, 1. We reshaped our whole our whole data set so that it is actually of this format, 28, 28, 1. The question mark here is basically for the batch size. Since we have not given any batch size, the batch size is right now question mark because the model does not know. We will be adding the batch size when we will be using the fit. Okay, and that is how it goes on. So this is our input. And this is the final output that we will be getting, question mark, 10. Question mark again represents the batch size and you will be getting 10 values for it each. So now you will be compiling the whole thing. Since this is a categorical categorical multi-class classification, so that is why what we will be doing is we will be using a loss as categorical, and our optimizers will be Adam because it is pretty much used for most optimizers, and it is pretty good optimizer itself. And then metric is accuracy. So now we will be running this model for 2 epochs. The reason why we are running this for 2 epochs is, well, you will see. So here we start the training. One thing that you should know is we have verbose equal to 1. So what that means is basically, see, you are getting all these outputs, right? Estimated time of completing, that is 5 seconds. You have a loss, you have accuracy, you have the number of training points it is running for, you have the first epoch of 2 epochs, you are training it on 60,000. So the whole thing, this whole data that you are getting as output, this is basically because of verbose equal to 1. So what that means is it verbally gives us, not verbally, but yeah, basically what that means is that you will get all these datas. So let's suppose you have a model, a very big model with more than this number of data sets, obviously a very large, deeper model. So in that case what will happen is, right, if you do not give this verbose equal to 1, you give a verbose equal to 0, you will have no idea what the model is performing like. So you will have no idea, and you will have to wait till the whole model has been trained. And suppose it takes 2 hours to train, so you have waited 2 hours, and then finally you turn out and you plot the model and you see, okay, it's not happening in the way you wanted it to. So with this idea here, when all of this is written is, you can see and understand, okay, so my loss is not decreasing, my accuracy is not increasing. So in that case, let me stop the model and start one more time, make the changes and start one more time instead of spending my 2 hours here. So hence you have this verbose equal to 1, and I always want you to remember to keep it as 1 and not to 0 or something else. Save the model saving is basically so that you do not have to run this every time, do not have to train it every time. Now this is a small thing, so you don't have to worry, but when it increases, obviously you do not want it to train every time. So now we do not usually plot the history or the loss and validation loss when you have only 2 epochs, but I am still plotting it out to show you. By the way, did you look here? You have an accuracy of 98%. If you remember, the last time we were talking about MLP, right? So when we did MLP, we had a lot of layers, and even then our accuracy came to around 90%. It did not increase more than that or something of that sort, right? So here you can see it has reached 98 even in the first try, so you can understand this. So 98 for only 2 epochs. By the way, we have just added only one convolution layer, we have not added more than one convolution layer. So you can now understand the power of convolution. So anytime you have tasks which are related to image, obviously go for convolutions. Now, so this basically plotting is done when you have more than 2 epochs, right? But I'm just plotting it to show you this is how training loss is decreasing, and this is how our validation loss is. So you have this, and then this is the thing for accuracy. So this is how it is increasing. Now since we have saved the model, let us load the model here. So let's say this is our X test, right? And we are randomly using 2. So X test 2 is 1. We can see this here, right? But now let us see if our model is able to understand that. So the first thing that we will be doing is reshaping the X test 2. So our batch size is 1 right now because we have only one image, so we are using that, and instead of 28,28 we will be using 28,28,1 because that is how we have shaped our whole input model as. See, our input was, if you remember here, 28,28,1, and then you had none here, none basically representing the batch size. Since we are using only one, so our batch size is 1, so we have shaped it to 1, 28,28, and then finally 1 because of the channel. So it is very important, right? So one thing that you should know is it is very, very important to change the shape of as required by the model. You should always fulfill all the criteria that are required by the model before actually giving any value, right? Now let us look into something else. So this is our 23rd value. So I'm just randomly using a number, right? See, I used a 23rd test and I got an output of 5. If I do not do np.argmax, right? If I just do model.predict, see, you are getting all these values. The highest is this one, 9.99 into 10 to the power minus 1, which is basically 0.99. So what this whole thing means is, right, it gives you all these probabilities that it belongs to a particular class. Like I said, even in softmax it gives all these values, and the actual values were 0, 0, 0, 0, and then 1, and then followed by other set of zeros, right? This was the whole actual thing. Here also, see, 2.8 into 10 to the power minus 10 is basically close to 0. All these values are basically close to 0 except for this. So you get a 99% chance because of softmax. You are actually getting the probabilities. So you are getting a 99% chance that this image belongs to a class 5. So the actual value should be something like this. The predicted values are something like this. They are very close enough because all these are very close to zeros, so they might as well be considered as 0. Then we are doing np.argmax, which means which argument value has the highest value. So this has the highest value, so what is the position of this? So you have 0, 1, 2, 3, 4, and then 5. So this is in the 5th place, so our highest value is 5, so we get the output of 5. So this is basically the whole thing. The whole point of teaching this is you need to understand how to create convolution layers, First that, and secondly you need to see what the difference a basic convolution or making sure of the dimensions of the image make in the model. So there you were getting close to 90% accuracy, right? Here you are getting 98%. That too using just 2 epochs, so which is a very great thing. So what we have done is we have now covered MNIST using CNN. So we have covered everything about a basic CNN model, and we have done that in the MNIST dataset, and we have understood the whole thing. So in the next class what we will do is we will talk how we can use transfer learning, so the code for transfer learning, and we will build an actual project this time. Okay, so all these were practical things just to understand the whole thing. You can obviously try it out, you will be getting all the here all the code and everything, but we will be going through transfer learning next. So that is it for today. I hope you enjoy it and keep learning.